Hi guys, make sure that you have your chapter 2 guided notes available and make sure that you contact me if you need any help with homework 1. So starting on chapter 2 here, graphical summaries of data. Real quick break, someone did ask me the difference between simple random sample and convenience sampling. They weren't clear on the difference there. So a simple random sample uses a structured method to help you be random, but it's some randomization process that's not codified. So it can be having computer generate random numbers, picking a name out of a hat, any kind of thing that would help you be random. Versus convenience sampling, there is no structure. So I go out and ask 50 people. I talk to my friends, right? It's almost anecdotal. All right, and then we've got 2.1, graphical summaries of qualitative data. So if we take a look at this data here, so 30 students were asked some qualitative questions with one quantitative question, their age. So we look through all this stuff. This is a lot of information. I don't see any distinct patterns at a glance. So I could find these things, like what is the gender ratio? What's the most common major? What states are these people from? But the easiest way for humans to absorb data quickly is graphically. We can look at a graph, we can understand the numbers, we can understand things, relations to each other by looking at graphs versus looking at just the pure data. We can't get a lot of information out of it quickly. So graphs are very useful for this purpose. One of the things you can do to help you make a graph is do a frequency distribution. So the frequency of a category is the number of times it occurs in the data set. A frequency distribution is a table that represents all the frequencies for each category. The proportion of observations in a category is the relative frequency of the category. So you can think of relative frequency as like the percentage of that category of the data. So looking at an example here, if there were 50 credit cards used and we look at their frequency, so 11 times out of the 50, MasterCard was used, 23 times out of the 50, a Visa was used, 9 times American Express, and 7 times Discover. If I want the relative frequency, I would do the frequency of the category divided by the total frequency. So in the case of MasterCard here, I would do 11 divided by 50 is 0.22. So that's 22% of the credit card uses was MasterCard. And we're going to represent relative frequency in a decimal form. Okay. So relative frequency will be like a percentage, but as a decimal. You can go ahead and calculate those out. A bar graph is a great thing to use for qualitative data. We use equally spaced bars to show, and you can see at a glance here, we can really digest which one had the most, which one had the least. And this would be very useful if there were a lot more than 4 categories, for example. It would make it very easy for us to absorb large amounts of information. You can also do bar graphs horizontally. It's helpful if the names of the categories are long, you can list them out a bit easier. So sometimes we want to do side-by-side bar graphs. These are extremely useful for changes over time and understanding different scores on things, monetary changes. Side-by-side bar graphs can be very useful. A pie chart is a favorite of students I've found. It's an alternative to the bar graph. It is for displaying qualitative data. It's very good for comparing relative frequency. You can look at it and you can see very clearly that Visa is almost half of the pie, things like that. So to summarize quantitative data. So remember, quantitative is like quantity. It's like a number. So when we do this, we usually make classes so that we kind of group numbers together because the numbers can be kind of spread out. And sometimes it looks better if we kind of group them like, 5 to 9 are going to be this one, and 9 to So classes cover a width of information. So if I break my groups up, let's say my first class is 0 to 4. So my class width is 5 then. All the zeros, all the ones, all the twos, all the threes, and all the fours, that's 5 different numbers, all of those would be counted in my first class. Then all of the fives, all of the sixes, all of the sevens, all of the eights, and all the nines will be counted in my second class. So each class width is 5. There are 5 category numbers that will go into this class. The lower limit is the lowest number included in your class. The upper limit is the highest number included in your class. And there should not be overlap between classes. You want to be very clear about which numbers go in which class. So if we're looking at more minute information here, here's an example using some decimals to two decimal places. All right, so you can see I want to count like 0 to 1, but that's 0 to 0.99. I'm not actually including 1 because 1 is going to be in the next category. And then it's 1 to 2, but 2 is not actually included in that second class. It's in the next one. So that's actually 1 to 1.99. So you can see how you would generate frequencies there when numbers might be spread out. You might have 0.23, 0.57, 0.6, and none of those numbers would stack up if I was trying to make a bar graph. But if I put them all in a group together, then I can kind of see, okay, well, there's 9 different values in between 0 and 1. So pulling them together into these groups can make it much nicer to look at. For quantitative data, we usually use a histogram. A histogram shows us the width of those classes. With a bar graph, you could make your bar any width for qualitative data. It didn't matter how wide your bar was. But with a histogram, we're actually going to show the width. We're going to say, okay, if I'm doing this data and my first class is between 0 and 1, I'm going to make my bar cover the bottom between 0 and 1 on a number line. So you can see here, each class has a width of 1, and the bar goes from 0 to 1, from 1 to 2, from 2 to 3. So there's extra information included here. You're actually showing what numbers we're talking about and how many values fell into that category. So too many classes provide too much detail. So this is if we tried to just kind of graph each one or try to graph them in very small categories. We get some information, we see some patterns, but it's kind of, we can't tell like what the actual overall feel of it is. It's very jagged. If we don't make enough classes, if we make them too broad, well, we kind of get the idea that most of them are between 0 and 2, but we don't get a lot of more information than that. So there are no good rules for choosing the number of classes. It really depends on the individual data and what you're trying to show. So it's usually better to have more classes than less, but you also want to look at like set your classes, kind of look to see what the graph looks like, and then adjust from there, because there's no hard and fast rule. It's what looks best to display your data. So I would like you to kind of do a compare and contrast here between these two graphs, see if you can spot similarities and differences, see how many vocabulary words you can assign to each graph, and we can talk about those in office hours or in class. So we're going to talk about the general shapes of histograms here. So a histogram is called symmetric if its right half is approximately its left half. As you can see in this graph here, it's not perfectly symmetric, like it doesn't perfectly line up side to side, but it's generally kind of the same shape, so that we call that symmetric. A histogram is called right tail skewed, or positively skewed, or skewed to the right if its tail is on the right side. Tail's off to the right side there. A histogram is skewed to the left if its tail is on the left side. So the short side, the one that's a long tail, that's the side it is skewed towards. A peak or high point is referred to as the mode. A histogram is unimodal if it has one mode. A histogram is bimodal if it has two clearly distinct modes. And sometimes this is a very interesting thing to see in your data. It usually means that you've actually got two subgroups in whatever you're studying, one that's like this and one that's like this, and they overlap there, causing it to be a little higher in the middle than it is on the two trailing sides, because it's actually two trailing sides added together. So that usually means that you have two groups. For example, maybe height. Maybe this is females and this is males, right? So their height might be higher on average for males, and the height might be lower on average for females. But there is some overlap here. But you can see that there's two clearly distinct groups. So bimodal is a very interesting occurrence if you see that in your data. A histogram is uniform if all the frequencies are approximately equal. If this happens, you don't have a lot to inform you. This isn't telling you much of anything. I would like you to go ahead and write down your thoughts on this. See if you can find the skew and think of an interpretation for that skew. And then we can talk about that in office hours or in class. Again, take a look at this graph, see if you can determine the skew and interpret what does that mean in the context of this data, and then we can discuss that in office hours or in class. This is called a stem and leaf plot. It's kind of like two bar graphs going at the same time. So actually, it's like a sideways histogram going here, okay? And then another sideways histogram going here. So that you can kind of compare these two things. So the history class, I can see that the center, the average of the hump, the mode there, is at a higher value than the center or the mode for this English class. Now, how do we read this actual data here? Like, what are these numbers saying? So it's actually, here's the English course data, and here's the history course data. And if we want to see who gets better scores, who has higher scores. So this 45 for the English class, someone scored 45%. That's this number here, 45. And then we've got a couple of different numbers. We've got 62, and then 66, and then 68, and then 69 happening here. So these numbers are actually 4 different values that occurred in the 60s. Okay, 62, 69, 66, and 68. Okay, so we can see that in the history class, the numbers tend to be higher, right? Not everyone scored higher than they did in English class, but the history classes, there was actually even one person who scored 100%. There were 3 people who scored in the 90s, right? So we can kind of get a good comparison going with this kind of graph, the stem and leaf plot. A dot plot consists of a graph where each value is plotted as a dot on a horizontal scale. Dots repeating values are stacked. This is best for quantitative data. That's that counting type of data, the discrete data, okay? So that like we can represent whole values with these dot plots. Time series is when you've got something that happens over time and you want to look at it that way. X-axis is always time. IQs of a sample of 31 adults are recorded, and this following histogram is constructed. Go ahead and give these problems a try, and then I can go over your results with you in office hours or in class. Go ahead and give these problems a try, and I can go over the results with you in class or in office hours. All right, graphs can be misleading. This depicts the number of votes in millions in the 2008 US presidential election. Please note that this gives an exaggerated difference, even though that's 10 million votes is a significant number. because they zoomed in to the tops of the graph. See how it starts at 50 million votes at the bottom there? It didn't start at 0. So it made it look like there's a big gap between the two graphs there, but it's actually pretty close together if you zoomed out. So the graph to the right here depicts the passenger train traffic at Denver International Airport. So when we look at the zoomed in one, the one where it starts at 47 million passengers at the bottom there, it looks like there's a huge difference between 2006 and 2012. And, you know, it's not an insignificant number. We're talking about numbers in the millions here. But when you zoom out and you really get a look at how close they really are compared to their total amounts, it doesn't look as significant. So having a non-zero axis is something to watch out for. It exaggerates differences. Not that those differences don't exist or aren't important, but that you want to get a feel of them in relation to a whole, right? Not in relation to just the difference. Another thing that can happen is if you're comparing graphs that are two-dimensional instead of one-dimensional. These bar graphs, they're really only one dimension. They go up and down, then that's it. If you're doing a picture graph, it actually has 2 dimensions, up and down and left and right. And when you when you make something larger, if you make it larger, the same difference left to right, you're over exaggerating what that is because of the difference a squared makes to a one-dimensional, right? So area being the issue there. All right, and I would love for you to look over this graph, see if you can find any problems with it that we can discuss during office hours or in class. All right, thank you guys. See you for the next one.